like this. So once again, let me repeat that the claim is that there are very few cases when a quiver has finite number of pairwise non-isomorphic indecomposable representations. And all those quivers are listed here. So there are infinitely many, two infinite series and 3 extra examples. So any orientation is fine. So whenever you put arrows on edges, you are done with having quiver, and anything is fine. Okay, so there are several proofs of the theorem. As I said, this is one of the fundamental results in the quiver's representation theory. What is somehow well, as I said, so the proofs are different. There are algebraic proofs and geometric proofs, and they use different tools. Let me find this. Sorry. Like this. Okay. In order, we'll prove it using some geometry of Quiver representations. And for that, let us start with discussing the object, which is of the fundamental importance for us. This is the so-called variety of representations. So let me write it down. So what is that? So let us, as usual, fix a quiver. And so we assume that Q has no oriented cycles. And Q is connected. Actually, this is maybe, sorry, let's first do not assume anything. Let's give the definition in the very general setup. And let us just fix D to be a dimension vector. So this is a vector in Z greater or equal to 0 to 0. So for each vertex, we are given number, di. And then we consider, by definition, E sub D. This is the variety of D-dimensional Q module. So let us actually give a more explicit description. So let us formulate this as a lemma, which says that ED is nothing but the direct sum over all arrows. And here this hom from K to G starting point of an arrow to K to the power D terminal point of an arrow. Okay, so well, actually nothing is written here. Well, just the proof is that the representation is kind of fixed as soon as all the maps are fixed. So in particular, corollary, what is the dimension of ED?
The sigma d s alpha times d t alpha.
Absolutely. Yes, so sum over alpha from Q1, ds of alpha, just because this is the dimension of the home space. So you see, this is actually a very simple space because just a vector space of the dimension ds alpha dt alpha, sum over all alpha, and what's important is the sum of home spaces. However, there is an extra structure on this space. So this extra structure is the action of the group. So let us define the group GD to be the product over all vertices. Here we put GL DI. Okay, so that's just the product of general linear groups corresponding to each of the vertices. So the claim is that GD acts naturally on ED via formula. So we have a collection of elements, I from Q0, and we apply it to our representation, which is prescribed by a collection of linear maps phi alpha. And the result is the collection G T of alpha phi alpha G S of alpha inverse overall. Okay, so just means that we somehow multiply the maps by our G's on the left and on the right. So let me give you an example. So suppose our Q is just A2 Quiver. So meaning that we have two vertices, one arrow, something like that. So this is the A2 Quiver. And then this is our Q. And now we have D, which is D1, D2. So this is our dimension vector. And then ED is nothing but the homomorphism space from KD1, KD2. So that's it. Now we want to study the action GLD1 and GLD2. So this is our group. And now let me ask you the following question. So what are the GD orbits on ED? So please raise your hand if you know the answer. Okay. Okay. Alex, can you tell us what's the answer here?
So either K will be sent to something, it will be sent to 0, if it will be sent to something like all non-zero, all zero maps are, so if we have dimensions, so for every dimension of the image, we can send that to any other of the same dimension. So
How
the
many orbits are there? So we want to describe the orbits, and the first question is how many orbits are there?
yeah, we should have
Say it again.
I thought if D1 is less than D2, then we should have D1 orbits.
Yes, and if D1 is greater than D2?
Then D2 orbits.
And what are the orbits? So how can we describe each orbit?
By the dimension of the image of the
map.
Yes.
So yeah, it's called the rank. Yes. So
the rank, yeah.
So the orbits. So this is our map alpha, or our arrow alpha. So the orbits are parameterized.
By the rank of alpha.
Yeah, by the rank of by alpha. So clearly we can act on the left and on the right, and then the rank is the only invariant we need. And so what is, let's continue this example in order to pass to a more general situation. So now let me ask you the following. So how many classes of, or let me rephrase it. So how to describe all pairwise non-isomorphic representations of A2 of dimension D. So while we are still in the same situation, so we have A2 and we have dimension D, which is D1, D2, and we are looking at all non-isomorphic, pairwise non-isomorphic representations of this quiver of this given dimension. So how can you say what are they? Yes, Igor, please.
They are isomorphic if and only if they are both lie in the same orbit, and that orbit is just all maps of fixed rank.
Yeah, you're right. So actually the answer is the same. So we'll prove in a minute this in general situation, but let us say that so the answer is the same. So meaning that two representations M and N are isomorphic if and only if rank of phi M alpha equals to the rank phi N alpha. So that's very easy to prove here. And but well, important remark, this is not true in general or general Quiver. So let us give an example, just not to have a wrong impression. So can you construct an example where all ranks of all maps are the same, but the representations are not isomorphic.
Maybe we should consider A3 to say.
Okay. Yes. What is D?
We can take at first, okay, we can take at first some direct sum of 2A2 to say K to
Yeah,
K.
what is D? So what dimension you want to take?
1 to 1 to say. Okay.
Okay. Okay, so the first representation is what?
K maps to K and K plus K maps to K.
Okay.
And then we can take to say from the left diagonal embedding to K2.
Like this, right?
Yeah. I don't know if we should. Okay, the left map is maps V to pair V.
Yeah, but as a representation, this is like indecomposable representation.
Okay,
One,
yes,
one, one,
yes.
yes, and then just simple representation at vertex 2, right?
Seems like there we have ranks both equal. All ranks are equal to 1, but compositions, ranks of compositions different.
Right. So we can see that the decomposition into indecomposables are different, therefore the representations are not isomorphic, but indeed, as you said, so we can compare the ranks of the composition and they are different. So, okay, but let's formulate the general lemma.
But what if we would compare all maps for all paths, and if we have two representations that have the same ranks for such maps, will they be isomorphic?
Yes, then it's true. Then it's true. So in particular, in type A3, you compare just the yes, but I'm sorry, but let me say, so what you said is true in the case of equi-oriented type AN. Yes, so let me write this as a remark. So for equi-oriented AN, i.e., so this is Quiver of this sort. It suffices to compare ranks of all the compositions. But in general, this is not true. So let's consider another example. Oops, sorry. So one more example. So let's consider A3, but non-equi-oriented. So the orientations of the arrow are opposite. And then definitely, again, the ranks are not enough. So the ranks are not enough to fix the representation. So we have to be careful. Okay. So now the lemma says that the GD orbits in ED are in one-to-one correspondence with the classes of isomorphic representation. Okay. So in other words, M is isomorphic to N if and only if there exists G in GD such that M is G. So the proof is rather naive. So I mean, so if so M is isomorphic to N is equivalent to the existence of the following diagram for each alpha I to J in Q1. So we have the following diagram, M I to M J phi alpha M and M Ni to Nj phi alpha N. So we need an isomorphism here. So let me denote by GI, here GJ. So this diagram should commute. And this is equivalent to saying that phi alpha, say N, equals to GI inverse phi alpha M GJ. And this is equivalent to saying that N is GM. Okay. So actually, this is just the rephrasement of the notion of being decomposable. Notion of or isomorphisms between two representations. Okay, so now, however, this is somewhat useful. So let us, as usual, denote by the stabilizer of some actually, okay, let me put it here. So those G from GD such that GM is M. Okay, so this is just the representations which somehow all the elements which do not change the representation. And so this is nothing but the group of automorphisms of M, right? So these are homomorphisms from M to itself, right? Okay, okay. Just to somehow make a connection between the standard notion from the theory of the action of the group on the space and the automorphism group of representation. So this is the stabilizer, and so of course this is the subgroup, a subgroup in our group GD. Okay, so now why this is somewhat important. So let me formulate this lemma. First of all, what is the dimension of the orbit. Yes, so we want to consider the orbit of our M, and it's just some subvariety, some subset inside the space ED. And then this is equals to the sum dimension GD minus dimension of automorphism group of M. So this is the first claim, and the second claim is that there is at most one top dimensional. So first of all, can you say me why the first claim is true?
Well, because the automorphism group is just the stabilizer.
So indeed, we have a map from the group GD to OFM, sending G to GM. And well, this is a vibration with fiber isomorphic. So the group out M. Okay. Therefore, we can write explicitly that the dimension of M equals the sum di squared minus dimension of out M. Okay. And what about the second claim? So the claim is that, so we know that the dimension of the orbit is some concrete number, yes, this one, the sum of di squared, minus the dimension of the automorphism group. So in particular, this means that the smaller the automorphism group is, the larger is the orbit, and vice versa. If the automorphism group is very large, then the orbit is very small. However, the question is, so we might want to look at the top dimensional orbits, so the kind of most kind of likely showing up isomorphic classes of representations. So the question is, what are there? Is it possible that there are two kind of likely classes of representations?
This statement is true.
Yeah.
Okay.
Yeah. So this is the claim of the lemma, yes. So, but can we somehow understand why this is true? So what we can say about a top dimensional orbit? How can it look like?
It should be open in our
Uh-huh.
in our
So top dimensional.
representation variety,
Mhm.
and to open subsets should have intersection, and if they intersect, they are equal because it's just orbital group.
And E D is irreducible. So D is a closure of OM for M from a top dimension orbit. So if OM equals ON equals ED, then M is isomorphic. So the only question why the first claim is true. So why a top dimensional orbit is open in EG? Igor, can you comment on that?
Maybe so it have no stabilizer, and condition to have a stabilizer is closed.
That's right. That's right. Okay.
I don't understand. It doesn't have a stabilizer,
Igor, can you please repeat?
so it's not closed. But why does that make it open?
So, can you repeat the question?
I didn't understand. You said it doesn't have a stabilizer, so it's not closed. But why does that make it open?
So if our orbit has a top dimension, so his automorphism group is trivial. And, so let's consider the let's consider all representations that have non-trivial automorphism. Automorphism group. So condition to have that automorphism is closed.
Okay.
Okay,
So let us maybe, yeah.
It's possible.
So let us look at this example.
What definition we use for irreducible? I even don't understand this.
So irreducible is that it can't be presented as a union of two closed subvarieties. Okay, so so an example of non-irreducible variety is xy equals 0. So this is non-irreducible. But ED is a homomorphism space, so it's just a affine space. So it cannot be. So it's impossible that ED cannot be written as a union of say A union B, where these guys are closed in ED.
Why?
Well, because this is just ED is just the affine space, A to the N. Yes, and what are the closed subspaces, subvarieties inside AN? Yeah, so they are defined by the polynomial equations. So in particular, their dimension is less than capital N. Yeah, so you can't write n-dimensional spaces union of two n-1 dimension. And so here in particular, if we have a top dimensional orbit, then the closure is ED, the whole thing. And so if you have another guy, then they have to intersect. These are orbits, and so there's no.
Sorry, by top dimensional orbit, we mean that its dimension is just from O orbit, or we mean that it is equal to sum of di squared.
Its dimension, so the top dimensional orbit means that you have, so our space where our group acts is ED, right?
Yes.
So therefore, the ED is the space where our orbits sits in. Yeah.
Well, why can't we have situation when we have like orbits, only orbits of dimension less than dimension of ED?
Yeah, but you see what's written here, that we have at most one top dimensional orbit.
Sorry. Okay.
We're not claiming anything else. We're just saying that it's at most one top dimensional orbit. So that's it. Just that you can't have two orbits of the top dimension. It's just a remark rather than a statement, but just to somehow look at this situation more closely.
And top dimensional orbit is open because of what? Sorry.
So if you have a top dimensional orbit, yeah, so this is the orbit of dimension equals to dimension of ED, right? So well, the condition of being of the orbit being of that dimension is closed. So this means that so if you write down the equation of the automorphism group, yes, so it would say that the dimension of the automorphism group should be equal to some concrete number. Yeah, so
yes.
So this is some closed condition. So this means that the we have some condition on M, and so so this some how to say some so what we say that the closure of this top dimensional variety is ED, but you just have some algebraic subspace, yes, inside the affine space, and you know that this algebraic subspace has the dimension coinciding with the dimension of the affine space. So there's no other way to this subspace being open. So I mean, this just once again the same observation that if you have some algebraic relations cutting out something non-trivial inside your affine space, then if it has dimension equal to the dimension of the whole thing, then the closure of this guy is the whole thing. So just because the condition on the automorphism group is are algebraic. So I mean, this is a kind of very special situation of more general case where you have a group acting on an irreducible variety, and then you just ask is it possible that there are two different orbits of top dimension? So the claim that it's impossible. So something like that you have your variety, and inside you have two orbits of, so in principle you can imagine something like you have two halves of this variety, and this is one orbit, this is another orbit of top dimension, but this is non-algebraic situation. So of course, in order to prove this in full details, you have to somehow work some more details, work out some more details here. But just that in the algebraic situation, there's no way to have orbit of the top dimension, which is not kind of open inside the whole thing. So,
okay, so we use the fact that
the action is algebraic. So,
and,
I mean, in coordinates, it's written by algebraic in terms of polynomials.
okay.
Okay. Good. So let me somehow maybe give you an example. So let me consider Q to be A2 and D to be say C. Let's see. 2, 2. Okay, so we have K2. We have to K2. So let us first recall what are the orbits in this situation. So first dimension of GD is what?
Oh,
Say it again. What's the dimension of GD?
yes, maybe 16.
No.
DL.
8.
Sorry?
8.
Dimension of GD is 8. It's 4 plus 4,
okay.
right?
Yeah.
Okay. So now what is the dimension of ED?
It's 4.
It's 4. It's 2 times 2. So this is 2 squared plus 2 squared. And this is 2 times 2. And now what are the orbits here? How many orbits do we have?
3 orbits.
3 orbits. So they correspond to ranks 0, 1, and 2. So we have orbits of the rank equals 0 and orbit rank equals 1 and orbit rank equals 2. So let's start with this case. So what is the dimension of the orbit rank equals 0? So please raise your hand if you know the answer. So what it is here? So Andrei, what is the orbit, the dimension of the orbit?
0, because it is just 1 point.
Absolutely. And the dimension of the automorphism of M?
Then, due to the formula, it should be 8.
Well, it's even without any formula, yes, because if your map is 0, then if you conjugate it with anything, then it's still 0, right? So, I mean, no way. Okay, so now let's do another one. So what's the dimension of the orbit rank equals 2?
It's 4.
Right. So simply because this means that our map should be just an isomorphism, yes, within the two-dimensional spaces, and it's clear that this is a general situation. The determinant is non-zero. And Andrei, this is exactly an example of the situation we've discussed before. So the condition on the open orbit is that the determinant of the map is non-zero, right? And this is somehow algebraic condition, and meaning that this is an open to. Okay, and the dimension of the automorphism group is what?
Also 8, just when the determinants are not 0.
Why 8?
Because when the determinant of the 2 times 2 matrices in GD are not 0, then
Say it again, please.
when the determinants of the matrices in GD acting on this orbit are not 0, then the orbit will present to itself.
Yeah, but you see, we take some representation from the orbit, and we are asking what are the elements of the group which somehow preserve this element.
So it should be 4, because we have one matrix that we multiply from the left and then another one from the right.
And this agrees with the claim that 4 plus 4 is 8.
Yeah.
And what about the last one? So we are looking at the rank 1. So what is the dimension of this orbit?
3, when the determinant is 0.
So everybody agrees?
Yeah.
Okay, and the dimension of the automorphism group?
Five.
So you see the picture is somewhat simple, but not completely trivial. So we have 3 orbits. One of them is a kind of the open one, 4-dimensional, another is just a point. And in between, you have only one orbit, which is 3-dimensional, and this is how it looks here. Okay, so let us do one computation or more general statement. So this is a lemma saying that suppose we have a non-split exact sequence 0 to L to num to 0. And we want to compare dimension of OM and dimension of OL plus N. So what do you think? What is larger?
Maybe the dimension of OL plus N is larger.
Okay, so everybody has the same opinion? So let's vote. So we have one vote for this direction. So what about other participants? So what do you think?
I think that dimension of stabilizer of M should be greater. So dimension of orbit should be less than dimension.
So you agree with this, yeah?
Yeah.
I suggest we look at an example above. So let's look at this case where D is 2 plus 2. So if rank is 0, so how does our representation look like? So how to write M is a direct sum of indecomposables.
We have like the one representation with that's two-dimensional that maps to something 0, and another representation that's 0-dimensional and it maps to something.
Yeah, but so what's the answer? How to write this as a direct sum of indecomposable representations? So what is this?
So it's the direct sum of these two representations.
So how many indecomposable summands are there?
Yeah, 4.
Yeah, so it's twice S1 plus twice S2. And if rank is 1, what is M?
So we have 3, like 1 0 and 0. And there's 2, and then the one that just maps 1 to 1.
Yeah. So can we now see what's happening here? So what orbit is larger? The rank 1 orbit is larger, yes? And so this means that the inequality should be in a different side, right? Okay. So if true at all, the smallest possible orbit is when all the maps are 0, and this corresponds to the most degenerate, so can't say most the representation with the maximal possible number of indecomposable summands. Okay. So this is our lemma. Good. So let's prove it. So our for alpha to 1, we can write the map phi m alpha in the following form. So we have a matrix somehow cut into 4 parts. So here I could say A alpha, here I put B alpha, here I put C alpha. Okay, so this corresponds to L, and this is M. So this is L. So for each I in Q0, so one has Li sitting in Mi, and Ni is isomorphic to Mi modulo Li, right? So this means that we can choose bases in such a way that the structure of our phi alpha is like given in this picture. So L is a subrepresentation and N is a quotient representation. Okay. Now, let us consider G, GL, G. So GI is given in the following form. So we take some parameter T from K star, so non-zero element from our field, and our GI is C times identity 0, 0, and identity once again, so like this. So this is our GI, and let us write G phi m alpha G inverse. So can you tell me what's that?
You should multiply C alpha by T.
Mm-hmm. Okay. So we know that there is an alpha such that C alpha is non-zero because the exact sequence is not split. So therefore, the action of G, the form T identity 0, 0 identity on M produces a new representation, a new point in ED, actually in OM, different from M. Okay, so this means that we have kind of one parameter subgroup inside the group GD, which produces new elements in the orbit OM, but does not produce anything new in the orbit of L plus M. So this means that the dimension of OM is at least one it's at least dim O n plus L. Okay, so this one parameter subgroup does not do anything with L plus n because somehow it's just scalars of identities on n and L. But it does produce something new for m. Okay, so once again, the example which is compatible with this lemma is that the smallest possible orbit corresponds to the orbit of a direct sum of simple modules. So it's the largest possible sum, largest direct sum possible. And the kind of less concrete, the largest possible orbit corresponds to the most general representation, so that you can't somehow write the sum of something. Yeah. Well, it's less concrete, but nevertheless. So okay, so now so any questions so far? So we'll move to the next. So just one important summary we need so far is that we have ED, and we have the action of GD, and we have the orbits OM corresponding to isomorphism classes of M. So this is what we'll need later on. And so if no questions, then let's move to another tool which is needed for the Gabriel's theorem, but also for many other applications. So this is what is called quadratic form of a Quiver. So let U be Quiver with no loops, oriented cycles. So then definition. So a quadratic form Q of x in Z to Q0 is defined by some xi squared I on Q0 minus some xi j, where I to j is an arrow. Okay. So let me give you an example. Maybe one remark first, that the orientation is not important. Yes, because the orientation enters in the second term, but you can see that we have product of the starting point of an arrow and the terminal point of an arrow, and this does not really changes if the orientation is changed. Okay. So an example. So Q is of the form this. Then q of x is x1 squared plus x2 squared plus x2 squared minus x1, x2 minus x2. So we have x1 here, x2 here, x2 here. Okay. So there are two reasons why this definition does make sense. So first of all, this one more remark that you take q of d, where d is the dimension vector, then this is the dimension of vd minus the dimension of ed. Okay, so far, somehow this difference does not make real sense, because you take the difference of the group acting on some space and the dimension of the space itself. So, well, sounds not too bad, but does not really mean anything reasonable. However, the next proposition is, well, maybe not that surprising, but still. So the proposition says as follows. So let M be a module of Q such that the dimension of M is D. So then we can compute Q of D, and this Q of D is expressed in a very concrete way. Namely, it's written as the dimension of the home space, M to M, minus the dimension of X space, M to M. Maybe before proving this proposition, let us compute some example. So let Q be just A2 Quiver. And let G be 1, 1. And let me take M to be S1 plus S2. So what is Q of D?
One.
Right. And what is dimension of MM?
Two.
Right. And what is the dimension of X? 1, 1, 1, MM. So since this is a kind of bit more complicated thing, so please raise your hand if you know what is this extension dimension, how to compute it. Okay, Dima knows. So we didn't practice this, so maybe it's worth discussing more details. So let's think for maybe a minute. So, yes, Alex, can you tell us?
So it should be that we send S2 to, it should be M2 where we send K to K, like the representation K to K where it's the identity, and then we send S2 to K and 0 to 0, and then we send to go from K to K, we send it to we send the first K to S1 and the second K to 0.
Yeah, so what is the conclusion? What is the dimension?
That it's one dimensional.
Yeah, so right. So what is
Because we have the direct sum and we have this one, and the direct sum will be 0, and then this one, and it's some linear combination.
yes. So
the vector space, it's one dimensional.
So we can say that extension between two S1s is 0. So there's no way to extend S1 by S1 non-trivially. And similarly, extension of S2, S2. And we have two other guys, S1, S2, and X, S2, S1. So which one is trivial and which is not?
So the first one is trivial, and this one is 0, and the bottom one is 1. Oh,
so Igor, Andrei, do we need to discuss this in more details?
Yes, I think I don't
agree.
So let's look first at this one. So we have two definitions of the X groups, right?
Sorry, why can't we even previous?
Okay, sure, absolutely. So I have a request which is valid for the whole course. If you have a question, you want to discuss something, just please ask and we'll do this. So these two.
I thought,
yeah?
so sorry, I thought we should obtain projective resolution and do everything we defined, but here probably it is more explicit way.
So you remember we had two definitions. One definition is via projective resolution, via the exact sequence. So we took home and we were trying to complete the sequence, the home functor to an exact one, yes? But another one was that we were looking at the sequences, the following form. So this is why it's called extension. So you try to find a module such that it has a submodule of the form S of 1, and the quotient module is again of the form S of 1. Okay? So this is why it's called extension. And the point is that the only extension of S1 by S1 is the direct sum of two S1s, right? Because it should have dimension 2, 0, and the only representation of dimension 2, 0 is a direct sum of two S1s. Okay, so therefore, this is the only extension, and meaning that the X group is just just 0. So there is only one extension. Okay, so similarly, we have a question about S2, S1, 0. Oops, S2, S2, 0. So again, this question mark is the direct sum of two S2s, which means that it's trivial. Okay. So now, what about the extension from with the submodule S2 and the quotient module S1. Does it exist?
It should have S1 as like submodule.
And S2 as a quotient module.
If we need S2 as quotient module, probably the map between vertices should be non-zero. So but if we want to have S1 as submodule, we should have zero map. Like
Yes, yes. So what is the conclusion?
that it shouldn't exist.
It's still only trivial, right? So only direct sum. And actually in our notation, the submodule in the XMN comes on the second place. So it means that, oops, what did I do? What did I do? Can you see my screen? So,
Yes.
okay, so, come on. So the submodule is the second module. So this is 0. Yes, so X, S2, S1 is the possibilities of extend S1 with S2. Okay. And now the most interesting thing is 0 to S2, 0 to S1. So does there exist a module which somehow not isomorphic to direct sum of S2 and S1, but can be put in between there in the question mark place?
At least we know dimensions, so we should analyze what map can be.
No, but let's first answer just, is it 0 or not? Is this X group trivial or it's not? So can we take here something which is not S1 plus S2?
Well, we can take P1.
Right. So this is a module of the form K to K, yes, with the identity. Andrei, do you agree?
Yes. Is it true that we always have map from S2 to just any module?
Well, I mean,
A2
but,
module, I mean.
yeah, but we need a module which is somehow which has a submodule S2 such that the quotient is S1, right? And here it is. And so in particular, it means that the X group is non-zero. right? So so the question is there anything else? So what are possible sequences of the form 0 S2 to M? So you remember that the class, we are looking at the classes and we are saying that two guys are equivalent if there is, we take this identity map, and we are looking at isomorphism phi here. So how many isomorphism or equivalence classes of phi are there? So how are they classified? So of course, M or N should be just a map, just a representation K to K, yes? So the only question is what can be the map here? Maybe I put G here. This is my phi. What can be the phi?
Maybe
Well,
0
any
or
scalar.
not.
Sorry, Dima, what did you say?
Any scalar.
Any scalar, right? So phi is in K. Okay. So this means that all isomorphic classes, yeah, Alex, some question?
It should not be a 0, right?
Why? It can be 0. So this would correspond to the trivial element of our group.
Ah.
Disallowed.
But any two non-zero cases are equivalent, right?
Any no, this is the point. They're not, because we need the, just let me circle this. So these are identity elements, right? So it means that you somehow, so if we have KK for M and we have KK, they put psi here, where psi and phi are different, right? So the S2 is fixed. Yes, so this means that here you should have the identity. Okay.
Maybe it should be on the for the right side.
Yes. For what do you mean for the right? This is our model. Yeah.
I thought the diagram should be commutative, but if the scalar is 0, then I don't see how it can be commutative.
Of course, this is what I'm saying, that if phi is non-psi, this diagram is not commutative. Yes?
Okay.
You're absolutely right. So it means that different scalars define different isoclasses or equivalent classes of sequences. Does this make sense?
Yeah.
So this means that this is just determined by a single parameter phi, and the parameter matters, and the X group is just our key. So if we were working over integers, this would be Z, but doesn't matter. So some questions? Okay, so anyway, it's time to stop now. I'll give you we'll start the next lecture with proving our proposition, but since this is not that somehow clear, so your homework will be to compute the X groups between indecomposable representations of equioriented of the Quiver of type AN equioriented. So I'll upload it on the web page, but just so here we computed the X between S1 and S2, and in general, so we can take two indecomposable representations of the equioriented type AN Quiver and try to compute what is the X groups. Okay, but I'll upload.
So also the group structure.
Also the group structure.
Mm.
Okay. So any questions?
I have a question about vector space structure on X in terms of extensions of
Yeah, it's a good question. So there's no vector space structure, but there is a structure of the additive group, abelian group. Yes, you remember we defined the sum of two X groups last time, and this is how to add up two representations or two extensions. However, well, here we see that there is also a structure of the vector space here, because we can somehow do something with maps. But in general, there is a structure of the abelian group.
But if you walk over field K, so we have a description of X in terms of projective resolution.
Yes.
So it should have structure of vector space. So
Yes.
maybe it could be, I don't know, if we have a extension, we should and we want to multiply it by some coefficient, we should multiply one of the arrow on that coefficient or divide.
Maybe you are right. So maybe indeed we can just yeah. So we don't, yeah, you're right. We are taking just one extension, and then we can, yeah, we can simply take the embedding scaled by some number. I think this would work. Yeah, so we have a sub representation. No, this doesn't work. It does work. So we have the same representation, but we can embed it in different way. Yes, so we can just multiply everything by a constant, right?
Yes.
And this would probably give us, so better we check, but it would give us probably the desired linear space structure. Yeah.
And it's better to not multiply but divide by the number, because
Why?
when we multiply by 0, we want to obtain the direct sum, but so our structure should be different, should be defined differently for trivial extension and for non-trivial.
Let's see. I think it should work. You see, so if we have a exact sequence L, M, and 0, and then so the arrows look like A alpha, B alpha, 0, C alpha, right? And then if we somehow multiply everything by t. Maybe it did divide. So we want here to take this t as a parameter, right? So in order this somehow to go. And then to compensate, yeah, maybe we have to divide. Yeah, you're right. So if t is very small, this guy C alpha t goes to 0, and this would lead to the direct sum module. And in order to get such a matrix, we have to divide the submodule basis by t. Okay.
Thank you.
Welcome. Further questions?
What we use precisely in for I don't understand what we use from fact that the map from JD to orbit or to ED is algebraic one. So how it helps?
So the question is as follows. So suppose you have a affine space, AN. And inside you have a subspace. Say O. And you know that O is cut out inside AN by some algebraic conditions. Something like determinant is non-zero.
It seems different from algebraic, like we have a algebraic map, which is like polynomial.
Yeah, but the question is, so suppose we have an M, yeah?
Okay.
Yes, and so the question is, so what is OM? Yes, how to describe OM inside AN? And the claim is that it is described by some polynomial equations or inequality or non-equations. I mean, something is non-zero. Something is non-zero.
Okay.
So the claim is that if you have a algebraic thing inside AN, and you know that this is of top dimension, then the closure of this thing is the whole AN. And the well, the reason, so the action of GD on M on ED is algebraic, so it's given by some algebraic conditions.
Okay, you mean just that map is like
yes,
algebraic?
Yes.
Okay.
So once again, I'm not claiming that what I'm saying is a proof. Definitely not. Yes, but I'm just referring to some theorems from algebraic geometry. Yes, but of course, so in order to work it out in details, well, some speculation is needed.
What is their formulation then?
Say it again.
What is how they can be formulated?
So suppose you have an algebraic group which acts on an irreducible algebraic variety.
Okay.
Suppose that you have an orbit of this group such that the dimension of this orbit coincides with the dimension of this variety. Then this orbit is open.
Okay.
Further questions? So I think you can look at the textbook of Winberg on the seminar on algebraic groups, and there are many, or in the book of Kirillov on Lie groups of Kirill Jr. And in both sources you can find, I think, this statement.
Okay, thank you.
So further questions? So if not, let me stop the screen sharing.